In a previous video, I talked about flipping a trick coin. And if the flip resulted in heads 7 out of 10 times versus 700 out of 1,000 times, both sets of those results are 70%, but the larger sample size of 700 out of 1,000 gives us the power to see the difference and a greater confidence that the difference we see is real. But a coin flip is just a binary response, heads or tails. So with a coin flip, we're looking for a difference in proportions. In the example, it's 70% versus 50%. So now let's visualize rolling this 20-sided die as a stand-in for a continuous variable. I mean, it isn't really, because it's got 20 discrete values and we're not going to get 14.83. But let's pretend that the die is continuous and somehow magically rounds to the nearest whole number. Now, copying the coin results, if we roll the die 10 times and 7 of the values were 11 or greater, which is, half those values, or turn it into binary basically, we wouldn't think it was a trick die. However, if we looked at the actual values and the 7 higher values were say a mix of 18s, 19s, and 20s, we'd immediately suspect something was afoot. Such a fun thing, afoot. With the same small sample size, we can differentiate with the continuous variable when we couldn't with a binary variable. And as you may have noticed, using continuous variable data not only allows us to analyze the values of the data, but the spread of those values as well. Further, in real product development situations, even more can be gleaned from continuous variable data. Now, I use the 20-sided die so I could directly compare it to the coin, right? Turn it binary for a moment. But as they say, there's 2 sides to every coin. How could I not go there? The 20-sided die has an even probabilistic distribution. That is, there's an even chance of getting each value, assuming it's not a trick die. Now, that's rare in things that we measure on products and in product development. The more realistic uneven distributions add another dimension, normal or otherwise, which can sometimes make continuous variables even more advantageous. Now, there are 3 different lessons packed in here. 1, dumbing down your data from continuous variable to pass-fail is bad. Done all the time. Don't do it. 2, continuous variables are more powerful than binary and categorical variables, and therefore require smaller sample sizes. And then 3, continuous variables provide more information than binary and categorical variables. Really, just try to get to true continuous variable data whenever possible.